In this video, we will be discussing annuities. There are many types of annuities, but for our purposes, we are going to consider an annuity to be, in general, an account where you make regular, ongoing deposits and you let the money sit there earning interest. The two examples that we will talk about most often are retirement accounts and an education savings account. For a retirement account, if you don't set money aside for retirement, whenever you retire, you will not have an income. There will be no money coming into your pocket. So you need to be certain that you are saving for retirement. And an annuity, again, is a broad term for a type of retirement account. You've heard the terms, I'm sure: 401k, Roth IRA, IRA, maybe a 403b, mutual funds, etc. Those are all types of annuities. And so again, annuity is a broad term for an account where you make regular ongoing deposits and let the money sit there earning interest. So the annuity formula is the biggest one that we have seen so far. So be prepared to very carefully write down all of these steps. So A is the future value. D is the regular deposit amount. And then we do have two sets of parentheses in here. So parenthesis, 1 plus interest rate over n raised to the nt power, and then subtract 1, end your parentheses, over r over n. And it's not going to hurt to put an extra set of parentheses around the denominator, especially if the calculator you're using does not have the ability to type the problem exactly like it looks when I just wrote it out. In that math print is what they call that the exponent looks like it's actually superscripted, that you can form the fractions and so forth. For our purposes, n is the number of times a deposit is made. Also equates to the number of times interest is calculated. But again, for our purposes, we're going to think of it as how many times we're depositing money every year. We're going to use this formula when you make regular deposits. Okay, so that could be monthly, it could be an annual, it could be quarterly, whatever it is, but that's when we're going to use an annuity formula, when we make regular deposits on an ongoing basis. This is not something that you do just occasionally, okay? For the purposes of our formula, we're going to be making these deposits on a set schedule, if you will. The annuity formula is the one you see here, and yes, it's kind of big and it can look a little intimidating at times. There are two sets of parentheses in the numerator, and do make sure you get both of those in place. So parenthesis and another parenthesis. Also, this -1 gets left off a lot by students, so please be sure you remember to include that. And in this formula, A is the future value, in other words, the total in the account years down the road. D is the regular deposit amount. R is your interest rate. N is how many times you are making your deposit every year, and then T is your time in years. We will use this formula when you make regular ongoing deposits. And that's when you'll know to use the annuity formula whenever we're working on problems in this section. In our first example, we are going to deposit $100 a month into a retirement account earning 8% interest for 30 years. The first question is how much money is in the account when you retire? And then secondly, we're going to figure out how much interest was earned. So first, we're going to take our annuity formula because, again, this is an ongoing monthly deposit. So we're making deposits at regular intervals. Just going to record that formula again. The more we write it, the more used to it we get. And our $100 a month is our deposit amount. It does say every month, and so that tells us N is 12. 8% interest is R, 30 years is our time. So replacing each of the variables with their value. And don't forget that -1 is part of the formula. That gets forgotten often. Again, one of the things on your calculator, when you have this exponent here of 12 times 30, go ahead and do that multiplication. In that case, it'll be 360. We're going to enter it that way. It just saves us a little bit of calculator finagling that we have to do. Now, on the next screen, I'm going to show you how I have calculated it, and you're going to see this exact formula typed in. And I used a website, it's also an app, called Desmos, and it is $35.94. Okay, that's how much would be in the account 30 years from now. But the follow-up question to this says how much interest is earned. So interest is going to be the total in the account minus what you put in, or the total amount of deposits made. So the total amount of money in the account is the $149,035.94, and the total that you deposited was $100 every single month for 30 years. Or if you want to multiply by 360, because that's the number of payments, that would be absolutely fine too. So what that means is when it comes to the amount of money that was out of your pocket, $36,000 is what you deposited, but $149,035.94 is what you ended up with. And so because of that, you earned $113,035.94 in interest. Not a bad deal. Okay, but remember, when it comes to saving for retirement, the only way you have money when you retire is if you save during your working years. If you can make $100 deposit every month for 30 years and end up with $113,000, imagine how much you could end up with if you deposited $500 or $1,000 a month into a retirement account. All right, so for the first example, you're going to deposit $100 a month in a retirement account, earning 8% interest for 30 years. How much money is in the account when you retire? So first of all, the $100 is our value for D. We are making that deposit every month, which tells us that N is 12. R is 8%. 30 years is our amount of time. So plugging those values into our formula, we will be able to determine A, the total in the account 30 years from now. So again, 8% interest every month for 30 years. And when you do this calculation, again, on your calculator, this 12 times 30 can sometimes be a little problematic in terms of entering it as a multiplication problem. And so I am going to go ahead and just make it a 360 and just get that part out of the way. And then when you type all of that into your calculator, and I do have something on the next screen that will show you how to do that. But as you go ahead and put all of that into your calculator, again, with all the parentheses, the exponents, the fractions, the whole 9 yards, you will find out that 30 years from now, your $100 a month for 30 years has turned into $149,035.94. And again, on the next screen, I will give you more information about how you can get that number if you're struggling on your calculator. The second part of this question, though, says how much interest was earned. So interest, remember, is the total in the account minus what we put in. So it's the total minus the total deposited. The total in the account is our $149,035.94. The total deposited is our $100 every month. So there's our 12 for 30 years. Whenever you figure out $100 a month every month for 30 years, you will find out that $36,000 of that came out of your pocket. The rest of it, everything on top of that $36,000, is the interest that you earned just by letting your money sit there and grow over time. And so although $36,000 came out of your pocket, you earned $113,000, $113,035.94 in interest, which is how you got to that $149,035.94 total in your account. On this screen, again, you can see where I typed this into a actually online graphing calculator, Desmos.com. There is a scientific calculator that Desmos offers, but this is the graphing calculator, and it is the one that I highly recommend, especially if you're struggling to get these answers on the calculator that you have. Desmos.com is able to be used for free. It costs nothing. And there is also an app that you can get if you don't like going to the website all the time. But this, the beauty of Desmos is you can see that you can type this problem in exactly as it appears on the paper. The parentheses, the fractions, the exponent that's raised up in the superscripted format, and then your answer pops up right here. And so I really, really do like Desmos, and I would recommend it if it's something, especially if you're struggling getting these answers on your calculator. The other thing I will point out is that the fraction bar pops in simply when you hit the division symbol. So if you're looking for a fraction bar, that's where. And then here it's a to the b is the exponent key. And that's how I get the 360. And then you've got the arrows here, left and right, that let you move up and down. This guy is the delete if you need that. Okay, moving on to the next example. Marta wants to have $1 million when she retires in 30 years. So how much does she need to deposit every quarter if her retirement account earns 6.8% interest? And then just like in the last problem, we will figure out how much interest Marta earned. So again, going through, she wants to have $1 million. That is the future value. 30 years is our time. How much does she need to deposit? That tells us we're looking for D. Every quarter, N is 4, if her account earns R, 6.8% interest. So we have $1 million for the value of A. We're looking for the value of D, 6.8% interest, making a quarterly deposit. Started looking at my R over N, and I wrote it as an R over N. I want to make sure that that is the value and not 0.068, there we go, over 4, and not the variable. And I've got just a little tiny bit of a dot there. We want to get rid of that. If I can, there we go. All right. Now, whenever you type this into the calculator, I do want you to be aware that this entire quantity over here is being multiplied by D. So whenever you calculate this whole thing, that is not the answer to the problem. That is the number you are multiplying by an unknown deposit amount to get to $1 million. Now again, I will show you the calculation on the next page, and I don't have all of the details written out. And I've discovered if I go to the next one, it doesn't let me backtrack. So I will tell you that this value that's highlighted there kind of in white is 385 point, and then there's a whole bunch of decimals that come after it. Okay. Now to solve for D, we want to divide both sides of the equation by that 385 and all those decimal point number to get to our total. Okay. When we do that, you will get to the deposit amount. The deposit amount, when you do $1 million divided by that roughly 385 and all the decimals, again, keep all of those there, you will find out that that total is $2,591.52, and that is her quarterly deposit amount. If she wants to have $1 million in 30 years, that's what she needs to set aside every quarter or 4 times a year. Now, in order to calculate the amount of interest, very much like we did in the last problem, the interest is the total in the account, future value, minus the total deposited. So the total in the account is $1 million, and the total deposited is the $2,591.52 every quarter for 30 years. So whenever we multiply the 2591.52 times the 3 and the 4 and the 30, or in other words 120 total payments, we find that Marta herself deposited $310,982.40. The rest of the money that gets her to the $1 million is the interest. So she earned $689,017.60 in interest. And this is actually a very realistic time frame, and it's a very realistic interest rate as well. A fairly moderate interest rate. So it is possible to set aside about $310,000 and then more than double that in interest alone. And again, this screen shows the calculation that I went through. So remember, in this problem, the D is what appeared there, and then there was $1 million over here that needed to be solved. And so as we got this value here, okay, that's the 385. I told you it was 385 and some decimal points. In order to solve for D, we have to do 1 million divided by that number. And that's exactly what happens here. 1 million divided by that number gives us the 2591.52, again rounding to the nearest penny, that she will need to deposit every quarter.